All right, so for today's lesson, we are starting our we're starting our next topic, I should say. So if you guys remember, we spent the first kind of section of this year looking at organic chemistry, and that organic chemistry is really important because it sets the foundation of knowledge to be able to do this internal. The good news is if you are struggling with organic chemistry, it does give you a little bit of time just to kind of wrap your head around some of the organic chemistry content. If you're struggling with organic chemistry, you can still very easily do well in this assessment without knowing your organic chemistry well. So do kind of keep that in mind. So what I want to start by talking about is defining what spectroscopy is. This is what the internal is all about. And with that, we're going to actually start looking at our first set of spectra data, which is known as the IR spectrum data, which is infrared. So I asked you guys to think about light and what you remember about light. You probably did that in the junior school. You might have done some light if you're doing some physics stuff. Thinking about the wavelengths and thinking about the electromagnetic spectrum. So what are some things you kind of remember about learning about light? The prism, yeah. So there was that prism, you shine some light into it, it's split, and then you have the Roy G. Biv kind of spread of colors.
I think it's like red to violet.
Yeah, red to violet, and that is the, do you guys remember what classification that is? Starts with a V. You're going to kick yourself when I tell you the word. Visible. A visible spectrum?
Yeah, the visible spectrum.
Calvin was like, oh. So yeah, visible spectrum, that's what we see. That's why we call it visible, and that's kind of a range of colors. There's also wavelengths that we have that are smaller, that have more energy, such as X-rays, and there's ones that are larger, such as the radio waves that we use to listen in our cars. So, the cool thing about this science technology is that it's using those electromagnetic spectrums to find things out about the molecules. So today, you're going to need your chemistry notes, a pen or pencil. I'll pass out the internal side pens. I just realized that you guys don't have that, but I have them in my storage. They're all good. And then you will need your device, but you won't need it till later. So, just FYI. Hopefully my clicker works. It is not working.
So you can use the wavelength to determine
what you have.
Really? So like what functional group and stuff?
Exactly.
Wow, that's cool.
Yeah. So first thing I'll do is I'll introduce this topic, and then I'll give you guys some notes on infrared. I know it's a little bit note heavy at the beginning, but I need to kind of just make sure you guys understand what we're doing, and then you guys will have a chance to start looking at these spectrums. I'm going to start giving you guys homework because I'm kind of concerned after the organic test, the progress. So the homework is going to be 2 parts. There'll be something for the internal that we're doing, and then I'm probably going to give you guys 1 organic question a week, just to keep you guys practicing that. I'm mindful also some of you guys want to do thermo as well, so I want to get that going. And with thermo, what we're going to be doing is, you guys saw the STEM Academy that Ms. Brooker has made for the year 12s, for those that are going into engineering? No? Okay, so we're starting a STEM Academy. She's taking care of the year 12s that are interested in going into engineering and also me. I will be taking the year 13s, and I'm going to be looking at those that are interested in going the health science kind of pathway, or those who want to sit an extra standard, because I'm mindful that health science requires you to have 18 credits, and so we're going to look at strategies to make sure you have one of your science subjects with 18. Does that make sense? So it'll be a mixture of those that are trying to do that at university, those that need some extra support. That's kind of what we're aiming for. But I'll give you more information about it next week. All right, so let's talk about what spec is. This is honestly my favorite out of all the standards. Not just year 13, but like everything I've taught, this is my absolute favorite one. It is an internal. It's 3 credits. Unfortunately, all of the level 3 internals are only worth 3 credits, which is why we have to rely on externals to get you guys enough credits. It is an exam, and there's no practical component to it. So the bad part about level 3 chemistry is that, unlike level 2, you don't have a lot of practicals, and you don't have a lot of practical-based assessments, which, you know, has its pros and cons. I call it an exam, but it's really more like a puzzle. This topic's really cool because it's not a matter of learning lots of information. It's about applying it, and it's really neat to kind of see it applied. So today, let me give you guys your checklist out. We're just starting with the IR Spectra. We'll probably spend about 2 lessons on it. It won't take you guys long to wrap your head around it. The other thing that I printed on here is the resource sheet that you'll be given for this assessment. You're going to be given the second half of that piece of paper, and you'll be given the periodic table. Now, obviously, we don't need to use the periodic table for a little while, but I want to make sure you have it. So, you guys are ready. All right. So with the IR Spectra, the things that we are taking off, I think is actually everything on there. And we're trying to build this skill set over a few lessons. So let's recap about spec. I know we've talked about it briefly in our Do Now. But basically, spectroscopy is looking at how we study light. We're thinking about the whole magnetic spectrum, and we're seeing how does light interact with matter. So for example, we know that light's interacting with my red jumper because all the light is hitting my red jumper. It's absorbing most of it, but it's not absorbing the red wavelength. That's bouncing off. It's bouncing into your eyes, and that's why you're seeing a red jumper. So that's what we're thinking about in this topic. And what we're going to be using is a spectrometer, and that helps us measure the interactions between the light and the object. Don't worry about copying all this down. It is on Google Classroom. I put the PowerPoint at the very least up. I decided not to print out booklets this time because I couldn't have enough time to kind of get everything organized, so I'm probably not going to have booklets this time around. But I will print out any notes that I think are urgent and essential. Cool. So that's what we're looking at. Here's a blown up picture of the electromagnetic spectrum, and I think it's neat to see because it helps kind of start you thinking about the purpose of it and the size of these different wavelengths. So we can only see the visible wavelengths of light. It's very narrow in the grand scheme of things. Different animals and organisms can see other ones. So some birds see ultraviolet. And that's
insects too.
And insects too. And so the flowers that they see will look different to what we see, which is really neat.
Almost was.
So the smaller the wavelength, the more energy it has. It can go all the way down to like the atomic level. You think about gamma radiation with the Hulk. You wouldn't survive that because it's nuclear radiation. But we use stuff like X-rays to see our bones. The ultraviolet wavelength is the stuff that we're worried about for skin cancer. So that's on that end of the spectrum. On the other end of the spectrum, the wavelengths can get larger and have lower energy. So you would see this as radio waves. That's how you can listen to music in your car. You also see these as microwaves, which is what's heating up our food. Infrared is the one we're going to be focusing on for the first spectra, and that's basically just before that kind of red area. Are we okay with that so far? Yeah.
Infrared's like your TV remote, right?
Yeah, that sort of stuff. So we can't see it. And also you can see how it affects temperature and things like that. Cool. So in this topic, there's going to be 3 different spectrums we will be using to figure out the molecule that we have. The first one's going to be infrared, and that's the one I'm going to start with. Then I'm going to go to something called nuclear magnetic resonance spectroscopy. So basically we're looking at the nucleus of the atom and what information that could have. We can actually do that with multiple atoms. So the one I'm teaching you will be carbon, but you can also do it with hydrogen. So if you go to university and you do the 100 level organic or intro to chemistry paper, especially for those doing biomed, you do the exact same thing, except they add the 4th spectra on it. That's the one with the hydrogens. The last one is technically not a spectrum, but we need to include it anyway because we're going to use that information, and that's called mass spec. This one I didn't do at university when I did my master's, but my friend who was doing her master's at the same time did that technology. So I do actually have quite a bit of experience, or not personal experience, but general knowledge about how that one works. So what you're going to be able to do is combine all 3 of those spectra together and figure out what organic molecule you have, which is really useful because 90% of chemicals are organic based. So yeah, that's kind of the overview. So if you guys remember last year, you remember how you did your ion identification flowcharts?
Yeah.
And then you figured out what you had?
Is it the same?
Better. You also remember how I was like, you need to know all your functional groups and how you identify them for organic chemistry?
Yeah.
All right. That's not how we do things actually as a scientist, because that gives us really limited information. Like, why would I just want to know what the function group is?
Then why do we learn that?
You learn it to understand the big overall process. You learn to, you do it so that way you know their properties. Yeah. So this is now kind of giving you more real world science.
Yeah.
So, or not real world, I'd say more actual what scientists do.
Yeah.
Sort of thing. So that's why I really like this standard. It's also, I think, the most useful standard going into university. All right. So the first one we're talking about is the infrared spec, and this one is the one that we are dealing with that is before the visible light. You don't need to know how the machine works. I'm just giving you some general overview so you're aware of it. But basically what happens is we have these molecules, I shine some light at it, and I'm seeing if the molecule is absorbing any of that light energy to see if it starts vibrating. And that's going to happen with those covalent bonds. So depending on that bond, it's going to influence then how it vibrates and how much energy it's going to take in. So that's kind of the first thing to kind of keep in mind. What we then see when we read the data is this IR Spectra kind of printout. So what you'll notice when you look at this is you have wavelengths on the bottom, and so that's the different size wavelengths, all of them falling under the infrared spectrum. The other thing you'll see is on the top here is the absorbance. So we're seeing how much of that light energy is absorbed, and that's what's then causing these little troughs. So if it absorbs a lot of that wavelength, it's going to be really deep troughs. If it doesn't, then it's going to stay up near zero. So we can use that to figure out what function groups we have, which is really neat. Cool. So, like I said, these bonds, for these covalent bonds, can be very stiff, but they're also can bend and stretch and bounce. And that will, they need to absorb a certain amount of energy to be able to do that. And they need to absorb that energy at a specific wavelength. So that's what is then going to be able to tell us what is their function group-wise. Yes. So some things that will affect it will be, actually I think that might be on the next slide. It will be affected by, the type of bond that you have, if it's double, single, triple, what atoms are involved in the bond. There's lots of different things that are used, or sorry, that will affect the absorption. And so we can use that as a fingerprint to then go, oh, that's what that function group is. So it's on this page here. So the covalent bond that I have, the type of bond that I have, and the mass of the atoms that I have. So all of those will influence what wavelength it'll absorb the light energy and how much of it it will absorb. So that's how we then create these unique fingerprints for each function group. And so instead of having to do those identification tests, you check out an IR Spectra and you can look at that graph and figure out, oh, this is what it has. So it's actually a lot more efficient than just doing a test and doing another test and doing another test. Cool. So I actually might switch to the board notes for this, and I'll pass out the examples of the IR spectra that we are looking at so you guys can kind of have a look at what the different function groups look like. So I am printing the notes that are critical.
So are we gonna make the graph?
No, so I will give you the graphs.
Oh, okay.
And you need to process the information from the graphs.
Yeah.
All right. So let me just switch to the document camera because I want to show you what these things look like. And I also want to get the resource sheet so you guys know how to start using it. And I'll get a piece of paper because I want to show you what I mean by how the infrared machine works.
You know the idea of that stuff.
All right, so when I did have a cuvette somewhere actually, just don't know where I had put it. I stole one from my lab. It's not working. Actually, let's steal it, isn't it?
That's kind of interesting.
Yeah. I'll have to find it and show you guys, because it's kind of neat just to see the actual equipment. Okay, so what happens is you have a little plastic container. Like that. So it's just a little plastic container that you have. And what you do is you put your sample inside the little plastic container. This plastic container, if you guys want to know the vocabulary, is called a cuvette. But you don't need to know that for the actual assessment. And in fact, you don't need to know how the machine works. I'm just trying to explain it so that way you have an understanding of what you're looking at. So I put my sample, that I don't know what it is, into a cuvette, and then I put it into the IR machine. And the IR machine is going to shine light at it. Say, for example, the red wavelength. And then, depending on what's in here, it'll absorb some of that light, or maybe it won't absorb any of the light. So then I have the amount of light that's left over. So in this case, this is a high percentage of something that's absorbing a lot of the light that's being shined. The machine will then go through and do another wavelength of the IR spectra. So it starts with the first one, it collects that data, it then shines a different wavelength at it, and then sees to see how much of it is absorbed or not absorbed. So it measures what's being looked at. So like in this case, it was like 60% being absorbed. Whereas in this case, 0% was being absorbed. So that's then what's going to translate into these data sheets that we see. Does that make sense? And it happens very quickly, and you wouldn't need to like manually input each wavelength to test. You just put it in the machine, you'd press a button, and it would shine the whole thing through. It would take a couple seconds, not even, and you would get the data. So then what happens is you, like I said, get those printouts like this. Now the main thing that we are going to be looking at is going to be basically 1500 and above, because that's really going to tell you function groups. It's very clear and easy to see the function groups in that area. This area here is known as the fingerprint region. You might be able to tell some things in there, but it can have a lot of background noise, so it's not a very reliable area for you to look, and I wouldn't be expecting you to really kind of point to things there and say, that's this function group. I would expect you over here to do that. Cool, I think that's all I want to kind of say about that so far. Something I do want to point out as two things to look for when you're looking at these IR spectra is look at 1500, so that way you know what's above 1500. The other thing that you should look for as kind of a reference point to try to kind of get you guys settled to know what's there and what isn't there is look at 1700 as well, and that's for your carbonyls. And the other thing is look at where 3000 is, because you should see the carbon-hydrogen absorption peak, because all organic molecules should have carbon and hydrogen as like a basic foundational stuff. So this is going to be something you can use as a reference point because certain function groups will be nearby it. Are we okay so far? All right. So each function group has a certain kind of pattern to where it would absorb light from, and this is just a list of characteristics. So you have a list of the different function groups and where you'd expect their absorptions to be. On your resource sheet, I've given that to you as well, so the yellow piece of paper, and you will have this on the assessment, so you don't need to worry about memorizing what function groups are where. So that's just one way to kind of look at it. The other way is this sheet here as well I've seen. And this one actually gives more description because it tells you what type of absorption you should expect, if it's going to be wide or very sharp. The other thing it'll tell you is the type of vibration, which isn't really useful because you don't have to write up and explain any of that. Are you okay so far?
So what's the difference between stretch and bending?
It's just the type of the vibration. So if we go back to the stretching and the scissoring, that sort of things. Yeah. So you don't, that's why I didn't give you guys this sheet, because you don't need to know the type of vibration that's happening. This bit here about the intensity is kind of useful, but I think you'll be able to see it on the graphs on their own. So I'll go through each one and I'll point out the things that you're looking for. And I'll give you guys some like hints and notes about what's likely to come up and what's unlikely to come up. And basically all the different function groups that we've talked about so far will be popping up on this IR Spectra. So I just want to give you guys some bearings of what to kind of look for. I do want to point out that each organic molecule will look slightly different. So they might all be carboxylic acids, but the carboxylic acids will look slightly different, but they will have a general thing that is very noticeable about them. You have to remember that these absorptions are going to be influenced by what else is around. So this is just like a general picture of what you're looking for. All right, so we're going to go through all our functional groups. So alkenes are the first one. Actually, I should say, do you guys want a break or you want me to keep going? Keep going? Okay. So the alkenes, if you guys remember, are the carbon with the double bonds. This one is unlikely for me to ask. And the reason why it's unlikely for me to ask is that it's very hard to see it with the IR Spectra. So it's not a really good one for me to use because there's nothing for you to really write down, and it could also cause further confusion down the line. So I just want to make sure you guys are aware that this is unlikely to come up. I'll give you a couple just so you can see it. And try some practice questions, but on the actual assessment, I won't give you an alkene because they're so hard to see. All right, so what I suggest you guys do whenever we're looking at these IR spectra is, like I said, 1500 is kind of where you want to look first, because you know you're supposed to be looking above 1500. We're not doing a lot of looking below 1500 because it's very hard to see anything from there. When it comes to the alkenes, you should see a peak or a trough, however you want to refer to it. And if I look here on the list, it says you should see this somewhere between 1630 and 1690. So this here is roughly, yeah, I would say just above, it's above 1600, but below 1700 on the scale. So it fits within the range of a C double bond C. So that is the identification peak for it. Now, it's really hard to see that one, and there's also going to be a lot of other IR spectra that will maybe have a peak there, and so it's not a very distinctive peak that you're looking for. So just be mindful. Like I said, I'm unlikely to ask this functional group because it's very hard to see it on the IR. The other thing you can look for is other information that is tied to the alkenes. So in this case here, we see the alkene, and we're looking specifically at a bond of the carbon to a hydrogen, and that carbon has a double bond. And so again, we can look here at the reference point, and it is mentioned, and you should see it around 3000 to 1300. And if I go down and look, it's about at 1300. So you see how things are supposed to, you know, generally match up where you're supposed to kind of find them on the resource sheet. Yeah? What else did I have to say about that? The other thing I would use as a reference point is the CH bonds. So it's roughly between 2850 and 1300. And so I can see that this is, you know, 2900, 2800. And so it's kind of in this region. So I can tell that this here actually is just your typical carbon-hydrogen bond. So it's a good thing to look for because that's a good kind of orientation to try to figure out where you are. So it's worth looking for. But like I said, it's very unlikely I will give you this one because it's these peaks, and when we see more of them, are very easily mistaken for background noise. So that's why I don't do this one. All right, are we okay? Keep moving. All right, this is gonna look like squiggles for a long time, and then eventually it's gonna stop looking like squiggles and it's gonna make sense. All right, so again, try to get some bearings about where you are. So that's 2000, so that's 1500, so 1700 is probably roughly around here. So I'm looking above that point. Again, it's useful to note where the CH is, so that way you can then see if it's above or below it. Remember that on the actual assessment, you guys won't have these things labeled. They're going to be blank. It's labeled there for now because it's using for teaching. So I see that basically around this area, That's where my carbon-hydrogen bonds are. With an with an alcohol group, you're going to have this wide trough, and this wide trough occurs between that oxygen-hydrogen bond. It's between 3,200 and 3,600. So it's this real kind of big thing that you're looking for that's just above the CH. So that there is what I would identify as your OH. Now, are alcohols the only one you see the OH on?
No.
No. So what other functional groups? Carboxylic acids are another one that you see the OH on.
Yeah.
So you got to be mindful that this here is helping me figure out that there's an OH there. I want to show you guys a carboxylic acid. Actually, should I show you the carbox? We'll go through some more functional groups and then I'll come back to it.
Cause like, does it show you like the whole molecule? Like,
Yeah, the whole organic molecule.
Even if the OH thing was like kind of in the middle,
It will still show it to you.
Like an alcohol.
Yeah.
Because it's not on the end.
Yeah.
Like a carboxylic.
Yeah. So you'll see when I give you guys the carboxylic acid one, what I mean by like how it has both.
Yeah.
So the other thing I'll show you then is the carbonyl. So if you guys remember, the carbonyl is the C double bond O.
Yeah.
Yeah. And again, we use 1700 as our, 1500 is our cutoff point to look above. Carbonyls are found at 1700. So this very sharp peak is a carbonyl. So that is my C double bond O. It'll be very sharp if you have it. And you can see in the last one, if I look at 1700, there's nothing here. So you see how on this one, if I look at it, I know it's an alcohol and not a carboxylic acid because there's no carbonyl in that peak.
Oh, yeah.
So you see what I'm saying?
Yeah.
So this one,
You'd have like the carboxylic acid if it had the carbon.
it would have both.
And the,
Yeah.
Yeah.
So this here is my carbonyl. Again, it's useful to look for that CH peak because you can look to the left and right of it. In the case, I look to the left and there's no giant trough here. So this tells me there's no OH. So no OH is kind of extra information. And don't worry, I'll talk about the justifications in another lesson. We'll spend, like I said, about 2 days on IR.
Yeah.
So yeah, that one tells me there's a carbonyl there. And if you guys think about the functional groups that we've learned, you know there's multiple functional groups that could have carbonyls. There's aldehydes, there's ketones, there's carboxylic acids, there's amides. So that's a lot of stuff that has carbonyl. So that's why we look to see if it has the other function groups as well. So in this case, there's only a carbonyl because I don't see anything else like the OH component. All right, here's another carbonyl. And I want to show you guys this carbonyl because sometimes, and this is a good example of seeing that even though these two are the same functional group, the carbonyl looks different. So you have to learn how to look for it in multiple ways because it's not the exact same fingerprint for the function group. So this here is my carbonyl. And again, we have 1500. We look up from 1500. That's at 1700.
Yeah.
So whenever I think 1700, that's the carbonyl that I'm looking for. C double bond C. And I look here, and that's my typical hydrogen carbon bond. So again, it's a very good kind of figuring out where you place. So this also is a carbonyl. So both this one and this one are carbonyls. They look slightly different, but the main thing you're looking for is a sharp peak for 1700. And that is a very deep, like sharp peak. We good? All right. Now let's start looking at carbonyls with other functional groups. So this one is an example of a carboxylic acid. So I can see that it has the carbonyl. It also has the OH. So like I said, use that reference point of that C, the carbon hydrogen. I look to the left, and in this case, I do actually see that absorption. So kind of like when you saw that one here for the alcohols. So we know that carboxylic acids would have both the OH and the carbonyl group. Because when we think about carboxylic acid, C double bond O, OH. So that's why we see the carbonyl and the OH. Does that make sense?
Yeah.
All right, some things that are different though. First off, it has both of them, so that's how I know it's a carboxylic acid. But the other thing that I'll notice when I look at these two, hopefully come on, document camera. Do you see how this one, for the alcohol, the OH trough is quite separate from the CH one?
Yeah, it is.
Whereas in the carboxylic acid, the OH one has actually moved down a bit, and it's now interfering with the CH one. So that's, again, what you're going to use to help you kind of decide, am I dealing with a carboxylic acid or am I dealing with an alcohol? And again, when you're looking at your reference sheet here, it should have some indications on where you'd see it. So you see how the OH can stretch slightly lower. It depends on what else is attached to it. All right, are we good so far? I know it's going to look like squiggly lines. It's going to look like squiggly lines for a while.
Yeah.
But once you get it, it's really easy. So all we're trying to do is figure out what functional group there is. Here's an acid chloride. So you know what that looks like. Again, the carbonyl. It's such a good thing to look for. The other thing is that CH, again, when I look to it, I see there's no other absorption going, so there's no OH. The other thing I want to point out to you guys, with the acid chlorides and with the haloalkanes in general, it's really hard to see halogens on IR. So I'll make that note. Very hard to see halogens. So that would be your haloalkane, sorry. On IR. They do have a note here at 600 that that's a chlorine and a carbon bond, but that's now in that fingerprint region that you guys wouldn't be looking for anyway. So just as a note, if we're thinking about looking for halogens, you're not going to find them on IR, you're going to find them on mass spec. So just kind of put a pin in that for now, because we're going to get to it when we do mass spec and you'll see how to find it. Are we okay with that? Be mindful that when we do these questions, sometimes I'll give you information like a list of potential molecules to choose from, or I'll give you an empirical formula, and that'll help hint what you're doing. All right, so let's now look at amides, because we know with amides, they also have that carbonyl. The thing with these amides, though, is that it really makes the carbonyl look really funny. So again, we still see 1700, but you see how this carbonyl peak is kind of wider?
Yeah.
So that's how I normally know if there's going to be an amide there, is that my carbonyl peak looks really kind of funky.
It's not as sharp.
It's not as sharp,
Yeah.
but that is still the C double bond O. The other thing I'm going to use as a reference point is that CH. Now I'm looking over here, and do you see how I see another trough? But you see how that trough does not merge with the CH one.
Yeah, like the alcohol.
Like the alcohol one. So this actually is your nitrogen-hydrogen absorption peak. That's what you're looking for. Now I call this one primary because the primary and the secondary actually do look different to each other. And again, everything should back up with the rough wavelengths that are given on this sheet. It's not going to be a perfect science, but it will be roughly in that zone. All right, keep going. All right, here are, since we talked about the amides, I want to show you what an amine looks like. So with the amine, when we go to 1700, right here, there's no C double bond C. I don't want you guys to think that that there is an example of a carbonyl, because it's not.
It goes like really.
It goes really down, and also this is slightly at 1600.
Yeah.
It's not quite at 1700. So it's like, it's a real kind of distinctive thing that you will see. So this one It's not something I want you to misidentify. And again, it's going to be a lot of practice that you guys are going to do to get it.
Yeah.
This one here, again, that's your CH1. Very good kind of, like I said, to help orientate you.
Yeah.
And then you look above and you see how you have an absorption peak and you see how it's a double one.
That one.
Yeah. So again, it's like what you saw with the amides, but it's not as deep.
Yeah.
So I'm missing 2 bits of information. I'm missing the carbonyl, and I noticed that the NH peak is not as deep. So these are all things you use to help.
NH, though?
It's still NH, because you have to remember amines and amides both have NH.
Yeah.
And in fact, this is going to be NH2.
Mm-hmm.
And hopefully my computer unfreezes so we can actually see what I'm writing. You might need to restart the program. Are we okay so far? I know I've been talking for a very long time and I'm sorry. I don't want to, I try not to, but there's a lot of function groups I'm trying to get you to see. Let's try to start it again. All right, there we go. So that one there. So if we see the difference in them. It's going to look like squiggles for a little while. All right, here is, okay, so now I want to show you the difference between a primary and a secondary amine. So this here is a primary. And you have to remember with the primary, you have a carbon, a nitrogen, a hydrogen, and a hydrogen. So you see how there's a double peak? It's because you have 2 nitrogen-hydrogen peak, 2 nitrogen-hydrogen bonds. Yeah? If you had a secondary, you'd have it in the same location, but it would just be the 1 peak. So if I was to draw that out, I would have carbon, nitrogen, carbon, hydrogen. So that's 1. Whereas this has 1, 2. So double peak, single peak. It's going to look really tiny. Now, one of the things to keep in mind is that sometimes this is really hard to see. And so you're going to have to use the other spectras to cross-verify each other. So if you're not sure if there's an amine here or an amide there, the way you can back it up, or like verify, double check, is your mass spec will have an odd number. So the mass of the molecule will be an odd number. So that's how you can verify it. So if you're not sure what it is, you can use that to help you make a decision. So all of the spectra we do need to talk to each other. Are we okay so far? It's going to look like squiggly lines for a long time. And then eventually it's just going to click, and then you're going to be able to see them without any issue. All right, cool. I'm just trying to think. That's the last one. So the last one I wanted to show you was just a secondary amide. So that way you know how to compare and contrast. And again, you can see the range of how funny they can look sometimes. And that's why we use the other spectra to back ourselves up. In this case, we look and we see that there's 1700 here. And this carbonyl is very yucky. It's not a very clean one.
Yeah.
But that is the carbonyl we're looking at. We have, again, that CH that we're looking for as our reference point. And then next to it, we have the NH peak. Now, since this is a secondary, it's only going to have the 1 peak instead of the double peak, or double trough, whatever you want to refer to it as. So the nice thing about the primary amines and amides is that they have that real distinctive double troughed. The problem with the secondaries is that they have only that 1 trough, and that makes it kind of hard to see because sometimes that could maybe be mistaken as an alcohol.
Yeah.
So just kind of keep that in mind. And that's why, like I said, you're going to use other spectra to help back you up. So like one of the things you look for is my mass spec number odd? And that will help you decide, do I actually have an alcohol or do I have an amide? The other thing is, if you have both the carbonyl and something here, you might go, ooh, then it's maybe a carboxylic acid. And so again, you're going to have some things that look funny. And so it could be mistaken as a carboxylic acid. So that's why, again, you have to use all the spectra to help you.
Yeah.
You shouldn't just be relying on one. The nice thing about IR, and the reason why we start with IR, it just helps you think about what could be there. It just narrows it down to a function group. We won't give you anything that will have 2 functional groups, I don't think, from memory. So we won't give you something that has a carbonyl and an alcohol, because that would be really hard, potentially. So it's going to be very straightforward function groups that we give.
Yeah.
All right. What questions do you have following that?
Are you gonna give us like examples?
Yeah. So you are going to do lots and lots of practice to see them. Let me zoom down. All right. So actually, I don't know if I haven't posted today's lesson. SciPads. The SciPad has a lot of pages in there about IR identification. I put 23 and 24 down, but you can actually, I think there's up to 28 is for the IR Spectra. You can skip 23 if you want, because it's just about how does the machine work. And we are never going to ask you a question on like that on the assessment. We want to see application. So that's something you can do. There's also an ESA questions as well, and I'll upload a worksheet as well. I'll post everything to Classroom, so that way you guys can see it, and you can just get lots and lots of practice to it. The other thing that I'll link on there is a website where you can actually look up molecules, and you can just have a chance to just look and see the variety of what their IR looks like. Yeah. But when it comes to the assessment, I'm going to pick stuff that have very clean IRs that make it easy to classify what it is. Or if it is a yucky IR, you're going to be able to find it from other information. Yeah. Okay? So I'll leave you to it. You guys have the rest of the period just to practice and understand this. I'll get you guys your internal SciPads. I know I haven't posted to the Classroom yet, so I'll do that as well. And so, yeah. So we'll do today, and next lesson we'll do also an IR as well. I want to show you guys how to justify it and what the Achieve Merit and Excellence justification looks like for IR. Cool. All right.
Miss, do you have a budget?
Yeah, all in those cans. All right. Before you guys run off, I'll just recap today's lesson. So just to recap, we were looking at defining spec and also processing infrared spectra data. We will do more of this in our next lesson, so that way you guys know what is expected for the write-up in this section of the internal. Make sure you do some of those SciPad pages. Just FYI, I've also linked this website, because Hannah, you were asking me about looking things up. Yeah. This website I've linked onto my lesson, and you can basically look up any molecule and you can see its IR, so you can get a variety of what it might look like. Oh, yeah. All right, spray the tables, put them up. Oh, sorry, put the chairs up. Sorry, I forgot to tell you guys to do that before the bell. Yeah.